All right, let's get right into it. We all know Jupiter is the king of the planets, right? But it turns out its auroras are hiding this wild secret that's completely changing how we understand space weather, not just on Jupiter, but, well, everywhere. And a brand new discovery has just blown the case wide open.
You've definitely seen pictures of the northern lights here on Earth, the aurora borealis. You know, those absolutely breathtaking, shimmering curtains of green and blue light. It's truly one of nature's most incredible shows, like a celestial ballet dancing across our polar skies.
But here's the thing. As beautiful as our auroras are, they are kind of tame compared to what's happening on Jupiter. The light shows there are bigger, way more powerful, and, as science have just figured out, they're powered by a kind of physics we have literally never seen before.
So, to really wrap our heads around just how strange Jupiter's auroras are, we first need a baseline. Let's do a quick recap of how our own familiar light show works right here on planet Earth.
It's a pretty straightforward cosmic recipe, really. You have charged particles, mostly from the sun, streaming towards us. Our planet's magnetic field acts like a giant funnel, guiding these particles down toward the poles. And when they slam into our atmosphere, that collision gets the gases all excited, causing them to glow and create those beautiful ring-shaped ribbons of light we see. Simple enough, right?
Okay, got that? Now let's head over to Jupiter and see how this all stacks up. Because everything we just covered, yeah, that gets turned up to 11. We are now entering the realm of what scientists are calling alien auroras.
And the differences are, well, they're staggering. While our auroras glow in visible light that we can see, Jupiter's are so energetic they're mostly invisible to us. They shine in ultraviolet and infrared light. They are just vastly more powerful, and their shape isn't some neat little ring either. Nope, they form these chaotic patches that are concentrated directly on the polar caps. It is so clear we are dealing with a completely different beast here.
So how in the world did we figure all this out? Well, we needed a detective on the scene. And that detective is NASA's Juno spacecraft. It's been our eyes and, more importantly, our ears at Jupiter since 2016.
Juno's mission is just incredibly clever. It flies in this long, looping orbit that takes it right over Jupiter's poles. This path lets it swoop in and get amazing measurements while spending as little time as possible inside the planet's crushingly intense radiation belts. And crucially, it's carrying this amazing instrument called WAVES. And this is really the key to the whole story. The WAVES instrument isn't a camera. You can think of it more like a microphone for electromagnetic signals. It allows Juno to actually listen to the radio waves that are produced by charged particles as they zip around in Jupiter's magnetic field. It's given us a totally new way to study the planet.
And by listening, Juno heard something completely unexpected. It detected a type of plasma wave that had never been seen before. A totally new piece of the cosmic puzzle that helps explain Jupiter's absolutely bizarre auroras. Okay, so before we get to the wave itself, let's do a quick refresher on plasma. You've got solids, liquids, and gases. Well, if you super energize a gas, its atoms actually break apart into this charged soup of electrons and ions, and that's plasma. It can flow kind of like a fluid, but because it's electrically charged, it gets pushed around by magnetic fields. And around Jupiter, the most magnetized planet in our entire solar system, the conditions are just extreme. The plasma density in the polar regions is incredibly low, but the magnetic field is unbelievably strong. This unique combination creates an environment where plasma starts to play by a whole new set of rules that are simply impossible to find here on Earth. So what Juno detected was this incredible transformation process. It starts with a wave type we actually know really well, called an Alfvén wave. But as this wave travels into that extreme Jovian environment, remember, low density, super strong magnetic field, it gets completely transformed. The conditions literally force it to change its very nature, and it morphs into a totally different kind of wave called a Langmuir mode. This is a type of plasma physics that had been theorized about, but no one had ever actually seen it happen, until now.
Okay, so we found a new wave around a distant planet. You might be thinking, cool story, but why does this really matter? Well, it turns out this discovery has implications that reach far, far beyond just Jupiter.
For one thing, understanding this new wave helps us to code the physics behind auroras on all sorts of other planets. It gives us a much better handle on how magnetic fields, the shields that protect planets from harmful radiation, actually work. And since these extreme conditions might be pretty common on, say, massive exoplanets or even on the surface of some stars, what we're learning at Jupiter could be the key to understanding countless other objects all across the cosmos.
And, ultimately it all comes back home. By studying the most extreme example of a planetary shield in our solar system, we learn fundamental lessons about the forces that keep our own world safe from that constant storm of radiation pouring out from the sun.
Think about it. This whole discovery was made not by seeing something, but by listening. It really makes you wonder, doesn't it? If Jupiter's environment can create entirely new physics that we can actually hear as waves, what other cosmic secrets, what other new symphonies of the universe are just out there, waiting for us to tune in and listen?